from National University of Singapore here. She's in the Department of Industrial Systems Engineering. Her PhD was from Cornell University, and she first was a professor, visiting professor at Purdue University in the Industrial Engineering Department there, and then after that she went to the National University of Singapore. So she's going to be talking about some multi-objective optimization methodologies that she's part of her research. Her research kind of spans many areas from optimization to simulation and other types of systems engineering problems.
Thank you, Michael. Thank you for coming this talk. This work is carried out with my postdoc, Jonghyun Ryu. This is a part of the stream of the research project, collaborative research project with the ExxonMobil Research and Engineering in New Jersey, the US. So they visited the National University of Singapore, and they approached me to launch this project. So the theme of this project is basically the simulation-based optimization. So let me first introduce what is the motivating example behind this project. So the motivation of overall this project is basically about the problem where the simulation is used to optimize very complex system. So one of the application the ExxonMobil has in their mind was this oil drilling operation problem. So once the oil platform is built, then there is a method called water flooding. So basically to the injector, they inject the water, and then they push the oil so that it comes out of the well. So but as you can see, basically the drilling and making a new well, and this is very expensive. So what they do is they have one project basically about developing the simulator for this oil reservoir, gas and oil reservoir. So what they do is that basically they simulate the water flow rate using the geology and also the fluid mechanics that governs the interaction between the oil reservoir and the water flow rate. So there are many goals in this problem. The most interesting goal will be definitely from the company's point of view is basically maximizing their profits. So how to maximize the production level. But there are two types of the goals in this way in this regards. One is the long term, basically over the lifetime of the reservoir, they want to maximize the production, and but also at the same time, daily they would also want to maintain some level of the production. But when they get the oil from the well, there is also a byproduct, which is the water. But this water is very contaminated, so they have to either dispose this water or they have to reprocess it. So they also want to minimize the max water flow rate. So there are many other types of goals, but these are the kind of the most important goals they have. So what do they do is basically they have a very complex simulator. So through this simulator model, they try to basically control the input. The second example is also water reservoir simulation. So basically in this case, what simulation doing is that basically the input is the water release rate, and the output is the water level. So probably people in civil engineering area might be familiar with this kind of example. So basically the policymakers, they want to put some policy or rules, like for example, what would be the minimum, the threshold level for the water release rate. So what they do is basically they try to find the best kind of rules or threshold through the water reservoir simulator. So what are the common thread in these two examples? So basically sorry about I have to talk about the objectives in this example. So basically the objectives would be they have some kind of economic objectives, like minimizing the cost, but at the same time they want to minimize also the water shortage, and there will be some other types of objectives. So the common thread in this example is that, so basically the rigor system is very expensive, so they have to, model this computer simulation model, and through this one they try to optimize the system. But this simulator is a completely black box. So what we can do is that basically we have these input vectors, and this simulation is completely black box, and we can only observe the output vectors. Okay. So typically these objectives, they are conflicting, and we basically cannot have any closed form for the objective function values. So basically we do not know what's the relationship between this decision vector and the output vector f. And also this simulation is usually very expensive, even though the computer has been developed quite a lot recently, but still it takes sometimes like several days to run the 1 or 2 simulations runs. So basically the goal is that we want to develop a new methodology, new method for this multi-objective simulation optimization, where we only can get observe the outputs for the responding to the input vectors. Okay, so let me talk about the basically the motivation of these projects. So when we started this project, basically the method they are interested in was derivative-free method. The reason is, as you can see in the previous slides, basically we cannot get closed form for this objective function, and so basically it's not possible to get a derivative. But still, using the outputs, we can also estimate the gradient using the finite difference method. But actually, in their applications, usually the output is noisy, or the output function is very bumpy, so that this finite difference gradient estimate is not really that useful. So they are basically interested in some derivative-free type of method. But for the multi-objective problems, actually in practice, the most popular method is the genetic algorithm or evolutionary algorithm. But yes, there are some convergence results for this kind of algorithm, like something called like a epsilon optimal type of convergence. But basically the ExxonMobil company, they want to have some mathematical method which can guarantee some type of convergence. So that's why we are interested in this mathematical derivative-free type of method. So let me first talk about the setup for the single objective case for this black box optimization. So this is very typical formulation for the optimization. So we have objective function, and the x is the feasible region. So in this case, we are either considering unconstrained problem, or constraint is very simple, like a box constraints. So again, the derivative is unknown, or basically unobservable. And so we can evaluate this f of x value using some very expensive simulation. Also, this problem can be extended to the stochastic case. So in that case, the psi is the random factor, and basically our goal is to optimize the expected value of this random function. But in this, though, we only focus on the deterministic case. But we have some work about also the stochastic case. Okay, so basically what is the goal in this project? So any other optimization algorithms, basically we want to find a good solution with a limited budget. So in this case, the budget is basically computed based on the number of function evaluations, because each evaluation is very expensive. So with the minimum the function evaluations, we want to get the best the solutions. So as I mentioned, basically when we started this project, the ExxonMobil was interested in developing a method which guarantees some type of convergence. So here we can talk about the 2 types of convergence, which is local and the global convergence. So local convergence, I mean here, is that basically we can guarantee that the algorithm converges to a first order critical point regardless of the starting location. And here, the global convergence means that basically the algorithm converges to truly the global solution. So the local convergence is kind of like a short-term performance, and the global convergence, basically to guarantee that eventually we have to explore the whole feasible region area. So it's like a very long-term performance. So usually it's not easy to achieve these two goals. So most of the algorithms for the nonlinear programming problem is basically guarantees the local convergence. So in another line of the research with ExxonMobil, what we are investigating is that how to decide whether and switch between the global search and the local search, so that we can eventually achieve the global solutions, but we can enhance the speed of the convergence using the local search. So that's another line of research with in this area. So basically in this work, we just first focus on the local convergence. But I'm going to talk about a little bit about the global convergence in the numerical experiment, how we can actually achieve it. So as the title says, in this work we focus, basically the method we are using is a trust region method. But before I mentioned that, basically the method we are interested in is the derivative-free method for the black box optimization problem. So in the derivative-free method, there are two famous methods. One is the trust region method, and the other is the drag search method. And at the beginning, the ExxonMobil, they actually suggested to use the drag search method because that's actually the method they are using for their actual problem, the real application problems. But for the single objective case, we observed it's working quite well. But for the multi-objective case, we thought that maybe the trust region method have some advantages. And actually, I'm going to talk about it later when I explain the algorithm. So in the drag search method, actually, there is a very famous method which is called BioMass. So that is the drag search method for the biobjective problems. So you can find, actually, this method is, you can find it in the MATLAB optimization package. But there is no method for the multi-objective or biobjective problems based on the trust region method. So that's why we decide to try this method. And we just apply this method very kind of sloppy heuristic way, and it worked well. So we decide eventually then how to design this the algorithm so that we can eventually guarantee the convergence. So let me first talk about the basic trust region method ideas for the single objective function. So we have here this is just a scalar function. So the blue line is the true function, and we have the black points. We evaluate the values at those points. So we choose we decide the trust region. So in this case, we just use basically this point, which gives the best function value. So around this point, we decide the trust region. So this is basically the trust region. And then we want to get the meta model within this region. So to construct a meta model, so we sample points within this trust region. So these 3 points are the new points. And then we, in this case, construct a quadratic model. Basically, the meta model should be something easy to optimize. And the region is usually not really huge, so quadratic model usually works well. So we use a quadratic model, and based on this quadratic meta model, we find the optimal solution, which is this. So this is the point, the new points. So we moved from here to here at one iteration. So this is the basic idea of trust region method. But there are many kind of other issues in designing this algorithm. So suppose that first we have the points which is improved compared to the previous iteration. Then what to do next? So the one option is basically we construct the trust region maybe around this new point and then keep moving on. But and also we need to decide the radius. So, but when we do that, the first thing we need to think about is that our meta model, is it really good or not? Is it really reliable or not? So we need to first test it. So we test trustability, the quality of the meta model using something called the reduction ratio. So basically, so we compare the response from the meta model and the function value. And if these two values are similar, then okay, this model is reliable. Then we move to the new points, and we actually keep the same radius or even expand the trust region radius. But if the model is not really good, then we just go back to the previous iteration, the point, and then we shrink the trust region radius so that we can have a better, reliable model. So this trust region method, basically how to determine the radius and how to move to the next two points, to be designed so that we can eventually guarantee the convergence. And there is extensive work for the single objective function case in the trust region method area. So if you go to the library, then there is a book, like a very thick book, the name trust region basically method. So this area has very, very deep history. Okay, so as I mentioned, there are some many issues, and particularly one of the issues is like what type of meta model should be used, and also how many samples should be collected at each trust region. So there are many issues, and there are many, based on it, there are many versions of trust region method. Also, there are the trust region method for the constraint optimization problems. But we couldn't find really the method for the multi-objective case. And actually, there are many issues when we apply this trust region method for the single objective problems to the multi-objective case, because we have now used the different notions of the optimality. So there are many kind of technical things that should be handled when we try to develop this new algorithm for the multi-objective case. So basically, our goal is developing the trust region-based method for the multi-objective optimization. Even though here I said multi-objective optimization, but actually our method is only for the objective case, and we are trying to extend it to the multi-objective case, but there is some technical issues when we do that. So let's talk about the settings for the multi-objective optimization. So we try to minimize the p different objective functions, and these p objective functions, usually they are conflicting each other. And as we assumed before, this is completely black box optimization, so these objective functions are unknown, and the derivative is not available. And in this case, we use basically the simple constraint or no constraint. And then now, how to define the optimal solutions in the multi-objective case. So some of you might be familiar with Pareto optimal solutions, but just for those who do not know about this area, so here is some short description about the Pareto optimality. So we are playing with, here is basically the image, the blue part is the image of the two objective function f1 and f2. So this is basically the image of the feasible region. And then we have some points within this feasible region, and y is just one reference point. And with respect to y, so basically the points in here is basically dominated by the y, and these points basically dominate the y. So these solutions are better than y. But when we look at these two areas, basically we cannot say that which one is better, because looking at the one function, maybe the value is better, but looking at the other function value, then not really better. So these solutions are basically not really compatible. So basically what we want to find is the solution which cannot be dominated by any, the points in this feasible region. And we collect all these non-dominate points, then this consists of this Pareto front. So basically the goal of this project is how to identify the solutions, Pareto optimal solutions, which consist of this, eventually the Pareto front line. this is for the biobjective case, so it's a line. So what type of algorithm we want to eventually achieve? So the things that we have to keep in mind when we design this algorithm is the two things. So first of all, the convergence. So at the beginning, we start with some set of solutions. It's a discrete set of solutions with approximate solutions. And as the algorithm process, we want to have eventually this set of the approximate solutions eventually converges to the true Pareto front. So that's the convergence we think. But if it converges, but eventually this discrete set of approximate solutions is close to only just to cover the part of the Pareto front, then we only can have information around this area. So eventually we want to have the solution which can spread out over the Pareto front line, so which is diversity. So we have to achieve these two goals at the same time. And as you can see, that actually this convergence is quite different from the single objective case, because the single objective case, you're looking at the sequence of solutions, but in this case, we are looking at a set of solutions. So there are many approaches for the multi-objective optimization, but probably the most popular way in the mathematical programming area is scalarization, which means that we basically convert multiple objective functions into one objective function. So what is the way to do that? The most popular way is this weighted sum approach. This is the most popular way. So it's just to simply take the weighted sum of the objective function and then solve this problem. But the problem with this approach is that you only can find the convex part of the Pareto front line. There are other methods called like a min-max or a min-norm, but the problem with this thing is that basically either you cannot detect some solution in a non-convex part, or the objective function is non-differentiable, so it's not easy to optimize this function. So the approach we are using in this work is called weighted product approach. So we are using this product form. So the R is some point which is in the image of the feasible region. And the advantage of this form is that it's differentiable. So for the biobjective case, this is it. So here we have a Pareto front line, and the R is the reference point. And we are looking at this function. So at the reference point, basically this function value is 0. And then as we move toward the Pareto front, this value decreases. So we move, and then until we hit the Pareto front. So by optimizing, minimizing this function, then we can identify this one. So by moving these reference functions, then we can identify the different solutions on the Pareto front line. Okay, so here I'm going to go over the step-by-step our algorithm. So like the typical trust region method, we first choose the initial point and the radius. So this is the initial center point and the radius. And then basically at the beginning, our approximate solution set is just to this center point. And here on the objective function space, we have this image of this disk here. So in the case iteration of the algorithm, we have the approximate solution set from the previous iteration. And we select the most isolated point. I don't go to the detail of this, but basically the idea is that we want to have the diversity in the solution. So the way we do is basically every iteration we choose the most isolated points. But at the same time, we want to expand toward the end of the Pareto front. So if other points are all close to each other, then eventually we choose the endpoints. So after we select the current iterate, the center point, then our reference point is basically this center point to construct the weighted product function. Okay, And the next, what we do is we build a quadratic regression model. So we sample the point within the trust region, and we build the quadratic model for the two functions, the first and the second objective functions, and the third one is basically the product of these two functions. So here we say that the fully linear quadratic models, let me talk about this a little bit detail. So the fully linear model means that basically we can satisfy these two conditions. So the errors on the objective function values between the true function and the metamodal function and the gradient, the difference basically can be upper bounded by the radius. So we should be able to achieve this one. So the one condition for obtaining the fully linear model is that basically using the at least 2n plus 1 points and then model the quadratic function. But actually the quadratic model usually to have the fully linear, the fully quadratic model, then actually we need a order of n squared points. But for the fully linear case, we only need the order of m points. So if we build the quadratic model based on this number of points, then basically the Hessian matrix is actually, we cannot uniquely define the Hessian function. So this Frobenius norm quadratic model means that we choose the quadratic function, quadratic model, basically which minimize the Hessian, the norm of the Hessian. So by having the minimum, the norm of the Hessian, we can have a kind of smooth function, so it doesn't have so much curvature. So that's the model we use actually in our implementation. But there will be many other ways you can build the meta models. Criticality checking step, this is a little bit technical, but basically what we are doing is this. We don't want to have a too narrow or too wide trust region. So too narrow is basically we are only focusing a very small area. But if it's too wide, then the issue is that the model may not be really good. The criticality checking step means that basically we want to control the radius based on the gradient function. So if the radius is, the gradient is too small, then it's too flat. So basically we cannot move them much even though we try to optimize the metamodal function. So in that case, basically we don't need to look at this huge area. So we just narrow down the radius of the trust region so that we can have enough kind of improvement in terms of the metamodal. So this one basically control how big the trust region should be. And also this condition is also very important for the convergence. But actually in practice, quite often people just skip this criticality step because it doesn't really often affect the overall performance of the algorithm. And then what we do is that basically we solve these three optimization problems. So we minimize the three meta models, and then we get these 3 points. So remember that to construct the meta model, we sample the points, and then we have these new 3 points. And the next step we need to do is that we check the models. So we need to get the reduction ratio for all the points. For the points we sampled to construct the meta model, basically we check the reduction ratio based on the weighted product function. But the other points, the minimization, we obtained by minimizing the meta models, then we use just those the corresponding functions. This is also something we needed to guarantee the convergence. So basically, we don't have an insufficient reduction ratio, then actually these points bother the convergence. So we exclude these samples eventually. But in real practice, actually, at the beginning of the iteration, these points in any case are very helpful because we can explore the wide regions. So beginning of the algorithm, we actually do not discard So we just include all these points. But later, after the algorithm progresses and we are near to the optimal solution, then these points actually bother the convergence, so we just discard them. And then we need to update the trust region radius. So for those newly sampled points to build the meta models, we just keep the same radius, or even we can expand the radius, because we never explored that the point before. But those points we obtained by solving the meta model optimization problems. Then we check the reduction ratio. So if the ratio is good enough, then we expand. But if the reduction ratio is not good enough, which means that the meta model is not good, then we shrink the trust region radius. And for other sets, the previous the points we collected previous iterations, then we just keep the same radius. And then obviously the next step is that we look at all the points, so newly collected points during this iteration and the points we obtained the previous iterations. Then we just screen out, and then we determine the new set of solutions. So these are the new solutions we obtained. Okay, so this is an important step. So now we have to determine if this iteration was successful or unsuccessful. So usually in the single objective case, this step is quite simple, just to look at the reduction ratio, and then we can define either it's successful or not. But in our case, we have a set of solutions. So how we can evaluate based on this set of solutions. So first of all, we must check if the trust region radius is greater than certain tolerance level. And then we look at the points we collect from these iterations, check if the reduction ratio is big enough, which means that in terms of which means that we can have enough improvement during these iterations, then it's successful. So if there is any points which can give enough reduction, then it's successful. But if none of these points can give enough reduction, then it's unsuccessful iterations. So this is basically this was the description of the algorithm, then how we can achieve the convergence. So let's talk about the convergence rate. And as I mentioned before, this convergence, showing the convergence rate is actually quite difficult to compare to the single objective problems. And even the convergence rate is even more difficult. So we couldn't achieve of course, the convergence rate. And as I mentioned, the difficulty of this convergence is that we are looking at the set of solutions. So the idealistic case is that basically we want to show that this discrete set of solution eventually converges to the true optimal part front. But the set of solutions is sometimes the set suddenly disappear. If you have a really good solution, then that point will dominate all other solutions. So suddenly you have like one point and they suddenly expand. So it's very difficult to find the connection between the solutions from the current iteration and the previous iteration. And even showing the diversity is even more difficult. But typically what people do is that for the diversity, people just collect some reference points here and then try to find the solutions corresponding to each reference point so that you can guarantee the diversity. So we did not really try to show the diversity, so we only just focus on the convergence. So the convergence we are showing is basically the limit point of this iterate. Only the center point eventually converges to the first order critical point of one of these functions. But the problem is that the f1 and f2, these are the fixed function, but f3, it changes every iteration. So for example, this is the center point, then the f3 function is based on this point. Constructed based on this point. But the next iteration we move to here, then the f3 function is now based on this point. So again, it's very hard to find a clear relationship between the current iterate and the previous iterate. But what we believe is that if we just trace this center point, since we try to choose the point which is most isolated every iteration, so eventually these points are all scattered around the over the Pareto front. So even if these points eventually converge to the one of the critical points, then we believe that basically over these iterations, iterates will converge to the over the Pareto front line. So, let me just briefly talk about the idea of the convergence. We just assume the typical assumptions for the single objective trust region method case. So the objective functions are Lipschitz continuous and gradient is also Lipschitz continuous. Hessian is uniformly bounded. And this condition basically means that we can guarantee the certain quantity of improvement in the meta models. And we assume that the Pareto optimal solution is bounded. So the first step is basically, this is the key part. Eventually the trust region radius converges to 0. So what is the idea? Actually this proof is quite technical, but the main idea is that here is our current iterate, the center point, and eventually we got this new point, and we have some improvement here. So we just look at the region between the Pareto front and the approximate Pareto front, and looking at this area. So if this improvement is always positive, then we have some contradiction, because this area eventually will, the area between these two cannot be below the level 0. So this area basically can be bounded, the lower bound of this area can be expressed as some function of the trust region radius. So if the radius always bounded away from 0, that means this area is always bounded away from 0. Then we have some contradiction. So that is basically the idea of this proof. So once we get that eventually this trust region radius converges to 0, then based on it, we can get this lemma. Basically what lemma says is that if the trust region goes to 0, then the gradient of the meta model also goes to 0. So that's the lemma. And then finally the theorem we want to show is that since the gradient of the meta model goes to 0, and by the fully linearity condition, as I described at the beginning, eventually the error between the true gradient and the meta model gradient is basically upper bounded by the trust region radius. So eventually the true gradient also should go to 0. So this is basically the local convergence, which means that we only can guarantee the local Pareto optimal solutions. Okay, so not really the global Pareto front.
Question. So the convergence you said was to one of the limit points of F1, F2, or F3, right? So if it converges to a limit point at either F1 or F2, that's almost like a single objective function, right? I mean, it's like if you just did a single objective. So
here, actually the meaning of this theorem is that in practice we have some tolerance rate. So this radius never goes to actually 0. And as I mentioned, the center point actually move around. So it looks for always the most isolated point. So it doesn't really stay always around the F1, the mean of the F1 or mean of the F2. It cannot. So it's just to move around all the time.
But the convergence result says it goes to one of the 3, though, right?
So what it means is that basically after, if the iteration k is really large enough, then the difference between, I mean basically, yeah, these points will be close to the F1, F2, or F3, the critical points. But we do not know, but what I mean is that these points cannot always stay around the critical point of for example, F1. It cannot, it must move around. Yeah. So Yeah, so I think it's better to looking at this one like some kind of, you see like some, the epsilon kind of optimal, point of view, instead of looking at, so what I mean is that basically this iterate doesn't always stay around the one of the critical point. It must move around. Okay, so the next part I want to present a numerical result. So we are using here basically two performance measures. One is a generational distance, which is basically looking at the distance between the approximate solutions and the true Pareto front. So we take the average of this distance. So that's GD. And the next one is a hypervolume. So we have some reference point here, and we are looking at the volume basically created by these approximate solutions. So if these points are closer to the Pareto front, then we have a bigger hypervolume. And as I mentioned, one of the most popular method, the derivative-free method for the biobjective problem is by mass. So we compare our method with by mass. Actually, we also compare our method to other generic algorithms, but we didn't present it because definitely these two methods are better than the generic algorithms. So the left one is our method. It's based on the 265 evaluations, and the right-hand side is 455. The reason is because we just believe that these two are kind of similar performance overall, but we use much less number of evaluations. And you can see the bias mass basically can cover around this area. The next case is the increase the number of evaluations, then basically we cover whole these regions, but with using the almost like a 2 times of function evaluations, but still cannot cover around this area. So this is the convex case. And the concave case, the same. We use 211, and then here is 463, and still ours looks better. And
do you have
then
any comparison when the boundary is not convex or concave?
sorry.
Do you have any comparison where the Pareto frontier is not convex or concave?
We actually, I didn't present it here, but we try many different types of Pareto front, like even disconnected case. And
but that's the main problem in many of the methods, right?
yes, yes. So actually, I'm going to talk about one of the things. So overall, whether it's convex or non-convex, as far as they are all connected, and there is only global Pareto front line, then our method works well, basically.
But do you have any examples that you show us where the boundary surface is not the Pareto boundary, particularly the true one? I don't care how simple the example is, but it's not convex. It has things like this.
Oh, so this is a non-convex case. This is a concave case. Or it does
it doesn't matter if it's convex or concave. The question is the same. If I have things like this or like this, what happens with your method?
It's still doing fine.
Sorry.
Okay, so I mean, unfortunately, I didn't bring it, but I can maybe send you our paper then.
But you understand the problem, right?
Yes, yes, yeah, I see what you mean. Yeah, but even we have also tried the disconnected case. You mean like even they are not connected?
The disconnected case is easier because if I know it's disconnected, then and both parts are convex, I can do that.
No, the disconnected but combination of convex and convex and non-convex. Yes. Okay. So one of the reasons that our method is doing well is that we sample the point within the trust region. And in the single objective case, usually we try to sample the point as little as possible. So as far as we have a good enough meta model, then that's enough. But in our case, we even try even select more number of points, but still works well. The reason is those points are actually helpful to identify the Pareto front. We are not looking for only just one single solution. We are looking for the solution in whole this area. So actually those points we sampled within the trust region, it helps for the exploration. Okay, so that's basically the advantage of our model, our method. Okay. So this one is basically to show that how empirically our method can achieve the diversity. So intentionally, we start from the point very near to the Pareto front. So we start around here, and then in the first iteration, we can already generate quite some points near the Pareto front. And second iteration, and then the third and fifth, basically, we can cover almost all the areas. So we can easily achieve the diversity, even although we don't actually show the proof, show the diversity mathematically. This is one of the issues that I want to address. So our method is basically the guaranteed local convergence. So here in this case, we have two local Pareto front. This is one. The true optimal, global optimal Pareto front is convex, and the local one is concave. So if we just apply our method, then basically we stuck in here. It's quite natural because we only guarantee the local convergence. So what we do is that basically that's what also BIOMAS are doing. So between every certain iteration, we intervene the algorithm, and then we run some kind of global search. So in this case, what we did is that basically we used the all already sampled points, and we also sample a little more points over the feasible region, and we construct a meta model, the global meta model, like using kriging or radial basis function, and then we look for.
What do you call this meta model?
Sorry?
What do you call this meta model?
You mean the meta model means?
I just finished the lab proposal, and to my frustration, they use meta model the way you use it and the way you use it in aerospace. The total abuse of the formal meaning of the word meta model. So basically, for you, meta model is any approximation of the model, or any surrogate model, or anything like that, right? Or any projection, or anything like that, right?
Mm-hmm.
Now, the only thing I want to bring to your attention is that at least in systems engineering, model-based system engineering, meta modeling has a very precise meaning of what meta models are.
Mm-hmm.
And you get this reaction from me because I have been totally frustrated to write this proposal, trying to go through all of these meanings of meta modeling in aerospace and engineering. And there is 90% ignorance of the fact that there is a beautiful theory based on logic of meta models that could be used here, and it will straighten up a lot of things and ambiguities. So I would object to anybody who uses kriging, projection, surrogate models, anything like that as meta models.
Okay,
So
then.
you are not the guilty party, but you see my frustration coming out of all these studies for about 2 weeks now.
Okay, maybe we can talk about it after the talk. But yeah, but I'm just using kind of, this is a kind of standard term in my area, so.
It's not only in your area.
Yeah.
And there are people here from my departments. It's also in aerospace, mechanical, and so on and so forth. And the major point why I bring it up is that they're missing the fact that in many of these studies, if you don't bring logic mathematics together with gradient mathematics, you're not doing a good job.
Mm-hmm.
That's the whole point.
Okay.
Because many design problems, we actually have both logical and continuous variables. But anyway, I made my point, and we'll discuss it later. So
Okay.
I won't call it meta modeling. I'll call it surrogate modeling, kriging, whatever you want to call it, that's fine with me. But please do not call it meta modeling.
Okay, then I will use the word.
Let's stop this propagation of terms that they don't really are accurate.
Then surrogate model will be fine?
Absolutely.
Okay. So we built a surrogate model like kriging or radial basis, like a global surrogate model, and then we solved that problem using the weighted product method. But we apply some because we know the closed form for the objective.
Do you use any of the gradient in computing your method together with kriging to actually improve the target model? Do you do that?
Actually, I have another research work. Yeah, not particular for this
So
one.
you do that?
Yes, yes. Yeah. Yeah, okay. So, as you can see, by introducing this global search, we can eventually identify the true global Pareto front. Okay, so we just apply this very heuristic way, like every 50 iteration, we just apply this global search. So definitely one potential research might be how we can combine this global search and the local search. We already have a work for the single object case, but not for the multi-objective case. So that's basically our future work. Unfortunately, we couldn't apply our model to the oil reservoir simulator because my student studied that the oil reservoir simulation system, but eventually the ExxonMobil didn't want us to use that because of the confidentiality issue, so we couldn't do it. But maybe I guess that they tried our model to that system, but we do not know the result because we are done with this project already by the last year. So here is the conclusion. So I introduced the method, derivative-free method for the biobjective problems based on the trust region method. So we could achieve the convergence, local convergence, and at the same time, empirically, we can achieve the diversity of the solution. So I present a numeric experiment. So I didn't present it, but we tried this method to many different types of the problems, and we can confidently say that our method at least works much better than the BIMAS. And we also working on the stochastic case. We have some theoretical results about the stochastic case, but to enhance the performance, one of the important issue is how to choose the sample size for the stochastic case. And we found that compared to the single objective case, it would be fine to use a small number of samples to evaluate the functions compared to the single objective. And we are trying to investigate these issues theoretically. So that's our current stage, and that's pretty much it for this talk. And this is the reference. So this paper is going to be appeared in Science Journals on Optimization. This here. And this is basically the work combining the global and the local search for the surrogate-based optimization. Okay, that's it.
Any further questions, John? Let me let Dave ask since John already.
I have two questions that sort of started back on your picture of the single objective function. If you could.
Okay.
Started there and it's stuck with me the rest of the time.
Oh, sorry about that. Okay.
So it seems to me that one of the reasons that your illustration here worked well was that you got lucky when you picked a trust region that bounded a piece of the function that was only second order, and you're using 3 points to think about it. So it seems like you've engineered a situation where you're likely to succeed. What would have happened if the actual function had been a 20th order polynomial in between those two reservoirs?
I think basically the model eventually will shrink the trust region, I think probably in that case, if the trust region can capture the overall trend, okay, so maybe the function can be very bumpy, but they might have some kind of overall trend. And if the trust region is wide enough to get the trend, then it will be fine. But if the trust region is already very small, and you have some area which has a lot of bumps, then maybe the method may not be really effective around that area.
So I had the same, if you go forward then to your illustration of converging from one Pareto frontier to the other.
Mm-hmm.
Can we go back to the previous one, actually? The previous one, you just 3 additional, but you actually used the other 2 points as well. You used 5 points in that example, right?
It depends on whether
Nothing to do with being parabolic honest.
you can use the
You don't have to just use 3 points also.
yeah, you can use the interpolation using 3 points, or you can also, because this is quadratic.
You can even do, some methods that do even bias estimates of the trust region, so it can be very general.
Yeah, so you can also use regression using 5 points. Yes, yeah, yeah. Okay, I think better. Okay.
So in your problem formulation, if I understood you correctly, you said you include box constraints.
Sorry?
You include
What?
box constraints.
Yes, box constraint.
But you didn't include, g of x is greater than 0. You put that aside.
So the thing is, basically this method is for the unconstrained case, and the box constraint.
So for an engineering problem, I mean,
Yeah.
let's be realistic here, right? I mean, you may have probably the number of constraints you're going to have could be orders of magnitude more than the number of design parameters.
Correct.
So discarding the constraints, I mean, actually that made me wonder, how the heck did you even get your feasible region if you didn't have any constraints?
Okay, so I'm not really expert for that. Okay, I first have to say that my area is more like, I think Michael knows that, simulation area. So this is basically probably my first paper in the deterministic optimization. But those problems, actually, when I talk with the Exxon, they also mention about those problems. But what they are doing is, what they do is, instead of trying to solve tackle the older constraint, they just use some kind of threshold for the constraints.
Threshold what? What threshold?
Sorry?
Threshold on what?
So basically, they just try to, as far as a certain threshold level is satisfied, then they are fine. So what they do is that they solve like a two-stage problem. So in the one stage, they try to identify a set of feasible solutions. And then they use these solutions to solve the actual their objective, to minimize the objective function. So that's what they do. But I'm not really expert in the area.
So have they done any work on you started out and you said, these simulations could go for days. And that's believable, right? I mean, it could be, you can imagine that happening. But surely, these guys are not stupid, right? They must be using multi-scale methods.
Yeah, so the thing is, so what I can say is that actually even the feasible region is not just by the simple deterministic constraint. Actually, it's a chance constraint, which means that the constraint should be satisfied with a certain probability because they introduce a sort of a stochastic randomness. So in that case, the chance constraint problem is even more difficult. So eventually the team, they try to find the method which can incorporate this chance constraint for this black box optimization problem. But the practitioner, what they're doing is that, as I mentioned, they just run the simulation and then they get the set of solutions which is briefly satisfy this chance constraint.
Yeah, but this doesn't give you any,
yeah.
I mean, we've seen that, but it doesn't give you any chance.
Yeah, so this is actually,
right?
yeah. So this was actually the motivation of this project at the beginning. So I also worked on some chance constraint problems, but I have to admit that our chance constraint is just one, very simple, case, like one or two chance constraint. But if we have like, hundreds of chance constraints, then we actually do not have any efficient method for that. I mean,
Has anybody tried to do preferential ordering of the traits? In other words, not all constraints or all metrics are equally important. So I could actually use logic to decide where I would do my first trades and then go and do the others. Has anybody doing anything like that?
I don't know, but maybe using some kind of ranking and selection method in the simulation can be used, I think.
Because there is a method that's called hierarchical or whatever it is that people use for biobjective optimization, and your stuff can be there.
Mm-hmm.
So has anyone done methods where, black box is pretty extreme. I mean, that basically says I have no clue what's going on the inside, right?
Yeah.
But people, they're engineers, right? Even if you choose a simple model
But
of the
it's
physics.
widely business schools. Come on, don't put it down.
But it seems,
Sorry. No, seriously, right? Even if you choose a very simple model of the physics, it's admittedly too simple.
There's no physics.
At least it gives you an idea about the way, you're not going to have functions of order 20, right? Physics doesn't work that way. Physics tends to be reasonably smooth. Okay, you have a few discontinuities, but it's not 20th order. So, have people designed algorithms to take advantage of that information?
No.
I do not know.
No. Can I ask a question?
But Dave actually was in the middle of the second question, right? Did you finish that?
Yeah,
Well,
so
the second question was sort of the same question, but applied to the sequence. Yeah, the sequence of.
So go to the graph where you saw the convergence in the Pareto. Oh, yeah, the sequence
Before.
the sequence.
you mean
You see a sequence of tubes converted back, right?
which
the
one?
lines that have
Earlier,
more
I
than one
think it's
inflection
earlier,
point.
the much earlier, yeah, the theory.
In your image,
Earlier,
and then
earlier.
if you wanna-
More further back, further.
Yeah,
there.
Right.
So again, I was wondering if you didn't get lucky because you somehow engineered a way for your approximate solutions to look very much like the final solution when you do not in fact know that the final solution looks like that. So you have, in this particular case, you have two inflection points on the final solution, and you have roughly the same number of inflection points on your approximate solutions. And what if that hadn't been the case?
So I think, so what you mean is that basically we do not know how the Pareto front look like.
Right.
So eventually we do not know whether our solution is really, close to it, and then.
In Mark's world, it would be very, very clean. It wouldn't have very many bumps on it.
Yeah, so basically that is the problem with this. So what people are trying to do is to avoid that situation is that, remember, once we got a reference point, and we can get the solution, Pareto front solution corresponding to reference point, which means that you just follow this line and then get this point. So if you can identify all these reference points and then you solve that problem, basically you just try to single objective problem until you find the corresponding, the Pareto optimal solution. So that's kind of the way that people try to make sure
What he's
that.
asking you is different, right? He's asking you whether you engineered it or you were lucky to have the critical points of the surface in all your approximations already.
Mhm.
So you have an example where, for instance, your first approximation will look like that, and then it will like this. That's what Dave is asking. Because here, if you look at it topologically, the three graphs, the three tubes, they're more or less the same inflection point. So what if I start with the first one, it looks like this, and then the other one is generated. Do you have any examples like this?
So you.
When you started very close to the line, you started close to the line already, you were able to find.
Yes, yes, we have that example I already presented. I mean, one of the cases basically, example would be this one. So in this case, basically, we start from very close, one point very close to the Pareto front, and then we can eventually generate all these points, even in one iteration. Yeah.
Because that's how you draw your trust region.
Yes, yes.
So the question is, right, it's the burning, right? A, in a real engineering design problem, you will never be able to compute Pareto points that you be confident that they are Pareto points. It's too expensive. And B, does this scale beyond 2? But like Mark said, I mean, the problems we face, they have hundreds of metrics, thousands of constraints, and millions of design variables. I mean, for instance, in aerospace or engineering and so forth. So how do you work yourself through this mess?
Well, I have to say that, I don't have any experience with such a kind of large-scale complex problems, because even this example, we spend quite hard time to find these examples in the literature, actually. Yeah. So if we could apply our method to the OE reservoir simulator, then that could have been really good, but we couldn't, unfortunately.
Is the accuracy of the trust region? In other words, how fat I'm going to make the trust region set or thinner?
Basically, the trust
This is
region.
controllable, right? So can you use that to get better results even with sacrificing some accuracy?
I mean, basically, trust region, eventually, your trust region radius for each point will give you some estimation about the accuracy of your solution. Yeah.
Well, all we care is, right, I mean, we don't really care in engineering. That's a mathematical problem, to try to find the true Pareto point, because that's fictitious. What we really care is to find reasonably enough trade-offs that we can propose as designs. And we are willing with that to carry, accuracies, or confidence, if you like, of the predictions. In other words, I'm willing to tell you, give me a fat tube of trust region, tell me that at least I have some reasonable trade-offs there. Not optimal, not Pareto or something, but reasonable trade-offs, so I can use them for my design, go on.
Something like maybe you can use like some, room like you can, like for example, epsilon optimality kind of condition like that. So it's not really, truly optimal, but
Have you
you
compared
can.
your method with something that's called multiple diversity maximization or minimization? Is your method in that category of algorithms?
Sorry, like which?
There's a method, right? There's a lot of theory, mathematical theory, on Pareto frontiers and the Pareto points, right? I mean, basically what it does is it says, suppose I knew some points that they are Pareto, and then it assumes, it tries to compare motions. Motion here means choosing a different design point, and compares the deltas, right? What happens to the metrics, right? Because, I mean, why do you like that Pareto point versus that? Because here, it's clear that it's the best trade-off between two, right? So people are trying to compare these deltas and see if I move here, what happens with delta. And that leads to an algorithm that's called, maximization of multidiversity or minimization of multidiversity, whatever you want to call it. Is your method in that category?
I am not familiar with that method, so I cannot say because
That's the one that uses in their software for simplex or log and so on, so forth, maximization, maximum diversity and so on. So forth.
because this is we have in mind like a very standard form of the multi-objective optimization problems, but I think it depends on how we formulate the problem, like the problem, the method you mentioned. Like it really depends on how we formulate the objective functions. Can be applied, I think.
All right,
One more question over
I
here.
just have one more question. So, when you do your iterations, when you show on the previous slide, you had not this previous, but the more abstract version where you have initial point and slowly converge
Yes.
over 3 lines to this.
Yeah.
On this numerical result, it seems like you keep on accumulating points here. So what's the connection there? Like, how does this picture connect with the later numerical result?
No, the thing is, in our numerical result, we didn't really show the every iteration what was the Pareto form. We didn't actually show that here.
For the next slide, you have 3 iterations, right? Yeah, this one, right?
Yes.
You have one, the first iteration and the second iteration.
So the thing is, here you can see that actually we start from the huge trust region radius, but because of the criticality step, we shrink. So that's why we have you see the series of the solutions along some line. Yeah.
So it's the first point.
First point is around here, but at the beginning the trust region is quite huge, and then eventually you shrink. So actually the first iteration doesn't mean that we are sampling points within just one trust region. Because of the criticality step, actually you can have several trust region and you collect points. So this is basically the example.
So did you go away from the
No, so basically starting from here, it was very huge trust region radius, and then eventually you have to shrink little by little. So you can see like the points are converging to this one. Yeah. So we didn't move, we just shrink the trust region radius. So by the sampling, basically, we could already identify all these points without doing any optimization.
But when you're talking about the reference point, that you mentioned, is that if you didn't start off?
So in this case, the reference point is basically this point.
It is.
So it's very close to the Pareto front, but still it can work.
But in a normal case, where you didn't know where the Pareto front is, and you start off, that would be somewhere else.
Yeah.
So that would be
Yes.
more likely than the first picture that you showed.
Yes, that's correct. Yes.
Okay, one more question? Okay. Last question, and we're running over, sir.
Okay. Can you move to the last on this? When you compare the global
Yes.
and the without global
Yes, yes.
yeah. How do you combine the global optimization with trust region method? Did you regress a global response service one time? Or did you regress the service every iteration of the trust?
So for this, at this stage, we apply a very heuristic, simple way. So just every 5th iteration, we just build a surrogate model, and then you fit it and do it. Yeah.
It's the rotation.
Yeah. But there should be some, way that we can, kind of cleverly do this switching between the global and local, but we haven't found any good way to do that for multi-objective, but we have some work for the single objective case. Yeah.
Can you still successfully jumps out from local optimal.
So when we jump, basically, also, I don't know if you are familiar with MES, the drag search method. They also incorporate the global search, but basically what they are doing is that they go to global search, and then the global model says that, okay, this is the best solution. Then basically you restart the local algorithm, basically. So it's like a multi-start algorithm.
But
Yeah.
this begs the question. Right? So what you need, right, to do that right, is what's called multi-level trade-offs. In other words, I have models that they are variable fidelity. I have, coarse, finer, finer, finer. And I'm trying to do trades exploiting that, because the coarse will give you some gross idea about trades, and then you can refine it. Because the problem I'm having with some of these graphs is you say I start close to the Pareto point. In engineering, we can't. We don't know. Like David said, okay, we are actually trying to come to reasonable trades. So I can't assume that.
Oh, but this case is just for
She was just illustrating diversity.
Yeah, but
Yeah.
I've read that. I looked at it.
Yeah, just the
I looked
basic-
at the papers. I mean, but I get no warm feeling, and it's not a criticism for you. I don't get any warm feeling that if I don't have any idea of where any trade-off point is, that this will lead me anywhere close to it.
Well,
But here is one comment. So, I mean, I don't mean. Okay, so this is one thing we found that when basically what other people BIOMES is doing is that trying to find the reference point and they eventually solve the single objective function to identify the corresponding Pareto front. But problem is we do not know how to identify. I mean, choose the reference point, because we do not know how the feasible, basically the image of the feasible region look like. So
listen. For two criteria, right? For two criteria, I can solve it in a minute. Here's what I do. I take your criteria, the two criteria, and in this case where you have no constraints, it's trivial. I'll take one criteria as a constraint and the other one as metric. I'll solve a million optimization problem doing the trivial thing, right? Take F1, minimize F1, where F2 has to be less than that, and I'll get you the Pareto point exactly. Yes or no?
well,
No, that's a theorem.
But he said he cannot do 1,000,000 points. The beginning, you have to be.
Yeah.
I mean, with current computers, I do this in less than a
No,
minute.
The very beginning of this
Yeah.
point was you'd only have a couple hundred
Yeah.
evaluation points at most.
Even with that, okay, whatever you have, I can do. Because how we teach multi-criteria optimization in optimization 101, right? We'd say take everything else, make it a constraint by putting an artificial bound, and then solve the primary metric, right? That gives you one point. You do it again and again and again for all possible combinations of the bounds, and that will get you exactly the Pareto point. We agree on that?
well, in this case, I don't think
Not in
it's
this
really
case.
that.
Answer my question for 101 optimization.
Yeah.
That will get to that. And then you say, well, that's not computationally feasible, so we need other methods. Now that will work no matter how many samples you have of the methods, as well as anything else, because it's exhaustive. The problem with our method is not that it doesn't work, is that it doesn't scale. So we need to be clever. Okay. So, I mean, what's the objection to that? Other than what I just said already, that it's not an efficient method. So for two criteria, with no constraints, I can do that any time.
Well, if that's the case, then I guess her argument would be MATLAB implements BIMED. Why would it implement that as opposed to your method?
Because they don't know what they're doing.
Okay.
They haven't taken 101 for years. Okay. Please tell them that. But all the students here that they've taken optimization system engineering from me, they will tell you that's in about 4 slides I have in my notes. And it works. Anyway. Thank you. Thank you very much.
Okay.
Thank you.
Thank you very much.